Okay, so this is second hour of Physics 1B for September 21st. We're continuing to talk about calorimetry problems that involve phase changes. So here's an example problem, also from your textbook. It says we've got a hot copper pot with a mass of 2 kilograms, including its copper lid, and it's at a temperature of 150 degrees Celsius. You pour, I really should draw a picture of these things, right? So we've got our copper pot, and into this, well, we know what its temperature is. It starts off at 150 degrees Celsius. You pour 0.1 kilograms of cool water into this. So we're going to pour 0.1 kilograms of water. And the water is at 25 degrees Celsius. And then we put a lid on it so that no steam can escape. We want to find the final temperature of the pot. So this whole system is now going to transition into a combination of find the final temperature of the pot and its contents, and determine the phase of the water, liquid, gas, or a mixture, and assume that no heat is lost to the surroundings. All right? So in the final state here, instead of having just liquid water, we could have... Ooh, why did I grab everything there? I don't know. The whole system is going to come to some final temperature now. So you're going to have some common temperature T, and the water is either going to be a mixture of vapor plus liquid, or it's going to be all vapor, or it's going to be all liquid. We'll have to figure out. So we'll have to figure out, like, what's the mass of steam? And we'll have to figure out what the mass of the water is as well. But we know whatever happens, that the whole system is going to be at the same final temperature. We have to do both. We have to figure out the final temperature and its contents, basically. All right? So this is a little bit trickier, right? Because there's a couple more unknowns. Let's go ahead and start off by writing down what we know. So we know what the copper... I guess the yellow looks okay on the screen. So we know for the copper that we start off with a mass that's equal to 2 kilograms. We also know its initial temperature. The initial temperature for the copper just these, I hate these subscripts on these problems so much. I'll just draw it a lot bigger. This is 2.0 kg. And then the initial temperature of the copper, that's a little easier to read, is 150. And then we've got the water. We know what the mass of the water is. And then we know the initial temperature of the water. That's all we really know, right? And then that they're put into thermal contact with each other and that they will eventually reach equilibrium. And we want to solve for all of these different variables here. Temperature, mass. So what should we do to start this one? What do y'all think? How should we get started? Some accuse. Certainly something we can do. Why don't you guys just try to work on it for a little bit and see if you start to figure out like what kind of things you need to think about. I'll specifically specific heat of copper we got to graph on this table. I think it's like 910. That's probably wrong though. Copper is 390. I don't know. Take a few minutes and just try to work it out for yourselves. I'll do the same. I already kind of know what needs to be done, but yeah, just try the sum of Qs, see what kind of unknowns you have, and see if you can figure out how to reduce the unknown somehow. I just saw your question, Tom. So you said, do we do the MC delta T for the steam as well? Maybe. I mean, so I don't want to say too much because I kind of want you guys to really think about it first. But there's multiple possibilities of what can occur here, right? So one possibility would be that the entire system heats up to like 100 degrees Celsius. Some of the water converts to steam, but the final temperature is 100 degrees Celsius, right? The latent heat of vaporization for water is this number right here. Any of these kind of questions that you just asked in the chat, I don't mean to be rude or anything, but you can definitely ask Google too. I know that can maybe sound kind of rude, but it's in your textbook. These are things you can look up on your own too, but I could have put it in here. 2256,000. Let's write that in here real quick. So then you've got this steam to water and the latent heat of vaporization. 2256,000. So a comma here and a comma there, and that's joules per kilogram. I think I wrote that right. Okay, so getting back to what I was saying, another possibility is that there is no phase change. That the whole system warms up to like, the water warms up to like 80 degrees Celsius, the copper cools down. That's one possibility too. And a third possibility would be that all of the water is converted into steam, and then the steam heats up to like, let's say 120 degrees Celsius, okay? So you have three possible final temperature configurations, right? Either the water is cooler than steam, so it's still water. Maybe it's like 80 degrees Celsius. There's a combination of water plus steam, which guarantees the final temperature is 100, right? Or the final temperature is like 120 degrees Celsius, and you have only steam left over in the container. Those are the three possibilities, and you kind of have to think about deciding for yourself how you know which one of those is going to happen. I don't know. Did that make sense, Tom? You said, do we do the MC delta T for steam as well? I don't know. You gotta look at the numbers in this problem first to figure out for yourself. It's kind of like one of those problems in Physics 1A where like you have a force applied to an object and you don't know if it's going to move because you're not sure if it can overcome static friction. It's really similar to that, actually. You've just got to see what kind of forces you have available. Like how much, in this case, how much energy is available from the copper compared to the energy needed to raise the temperature of the water to 100. Okay, so if you did that, Kenny, if you solve for the final temperature by ignoring the latent heat equation, and then made the assumption that it was all steam, you never took into account the heat needed to transform the water to the steam. So that's fundamentally flawed. But that tells you something, Kenny, right? It tells you something. If you made the assumption, it's not wrong what you did, but you made the assumption that you just said, okay, let's just figure out what the final temperature would be. Let's ignore the phase change process. And you got final temperature was 106 degrees Celsius, and you think, well, that's not reasonable, right? Because now that's 106 degrees Celsius water, and it's not possible to have water that's 106 degrees Celsius at STP, or at center pressure. So that means that some of it must get converted to steam, Kenny, right? And that last 6 degrees Celsius change is actually going to be a conversion of water into steam, right? Yeah, like Tom is saying, the line here is really long in this equation. So if the water manages to get to point D, right here, then at that point, you've got to put a ton of energy to actually make it go all into steam. A ton of energy. And if you compare the amount of energy to go from here to here versus the amount of energy to go from here to here, I don't even know if this is to scale, but there's another book. Yeah. So I don't know. I don't know what to think of this, but this is another picture of the exact same thing here. Let's zoom in a little bit. This one is from a textbook that I find to be fundamentally just better in all ways. This one is to scale, and it has energy added here on the bottom. And now you can see that the energy needed to go from here to here. Now this is specifically 1 gram of water, but the energy needed to go from here to here compared to the energy needed to go from here to here, it's significantly different than the previous picture. And these slopes are actually a little more accurate too, I think. Yeah, what do I know? So yeah. Okay, so I've said a lot of stuff. Let me give you guys a few more minutes and you tell me how you're doing. Did anyone get an answer yet, by the way? All right, I'll let you keep thinking. Okay, was that enough time? Did anyone get an answer yet? I think that's right. That's the right answer, Tyler. Good job. Okay, so let's just work through this. So we can kind of skip a step here because Kenny already told us that if we assume that it's all going to be water at the end of the day, and we just do this process. You do Q water to go from from 25 up to some final temperature T, and we add to that the heat needed to go into the copper to take it from 150 degrees to some temperature T, and set that equal to 0. This yields the answer that T was equal to, he said, 106 degrees Celsius, and I believe that's correct. So this is not right because this is higher than the temperature of water, liquid water. It implies that some of the water at least must be steam. So, if we know now that some of the water is steam, what does that mean about the final temperature? Do we know what it is? If you have a mixture of steam and water, what does the final temperature have to be equal to? It has to be 100 degrees Celsius, exactly. It has to be 100, not 106, but exactly 100. So if we know this, the problem is much easier to solve, because now what we can do is we can do the process again, but we can make it so that we add one additional step in here. Okay, I'm just going to copy this to make it go a little faster here. So what we'll do is we'll just say the temperature T is no longer T. We know what it is. And in addition, we're going to add one more term in here. So the water is going to go from 25 to 100. This is going to go from 150 to 100. And the new term we need to add in here is the mass of the water. No, not the mass of the water, sorry. We want to know the mass of whatever actually converts. So this is going to be the mass of, steam, basically. The amount of water that actually converts into steam, multiplied by the latent heat of fusion or the latent heat of vaporization for water. This M right here is going to represent the mass of the steam that we actually get, as the rest of the water will still just be in liquid form. Okay? So let's calculate these. So we've got Q water, that's going to be the MC delta key equations. So we're going to have mass of water multiplied by specific heat of water times our temperature change, which is final minus initial, so 100 minus 25, plus, for this one again, MC delta T, so mass of copper times the specific heat of copper multiplied by its temperature change. Its final temperature is 100 minus 150. And this should all be equal to negative M times LV. So to solve for this, we just need to solve for M. So additionally, another way to go about this is you could just literally calculate what this quantity right here is. So you've got the mass of water as 0.1. I mean, I'll write them in, but the first thing I did was just to just calculate this quantity right here. So 4190. Every single time I write a unit like this down, this unit is awful. Joules per kilogram degree Celsius. I hate writing that. Every single time I do that, I wish I had gone into mathematics instead of physics, so I could just not have to have units all the time. This is times 75. Mass of copper is 2. Specific heat of copper is 390. Times 50. This is negative 50, right? That's equal to the mass that we're searching for. And I'm just going to divide the negative LV down here. So divide by negative and then put the latent heat of fusion. So I'm just going to write it as 2.256 times 10 to the 6th joules per kilogram. And that'll give us the mass. So initially what I did was I just calculated these numbers, and I'm going to write them in so that you can see it for yourself. So if you calculate the first term here, the Q for the water, I get 31,425. And for this one, I got negative 39,000. Okay, did I actually round on that one, or is that really what the number was? No, that's exactly 39,000. 2 times 390 times 50 is exactly 39,000. And then we're dividing that by 2.2 million. There's a couple things you notice from this here. From actually looking at the numbers, at least I do. So the first thing I did was I just said, what would happen if I make the assumption that the final temperature is 100, right? What if I just make this assumption that there's going to be a mixture of steam and water? What does that lead to? And then you say, okay, well, we start off with Q water. What's Q water? The energy needed to take the water from 25 to 100 degrees Celsius. How much energy is that? This right here, right? That's the energy needed to heat the water up, right? 31,425 joules. And then I say, how much energy do I have available? The energy available would be the energy coming from the copper, right? The copper, if I take the Q for the copper to go to 100 degrees Celsius, I get negative 39,000 joules. And then you notice there's a difference, right? You've got some leftover energy. Does that make sense? It's like this is the energy needed to heat the water up. This is the energy transfer that would come from the copper, negative because it's cooling down. So that means there's about 7,500 joules of energy that can go into phase change, right? And so that's 7,500 joules. You just take that and you divide by the latent heat of fusion, latent heat of vaporization of water, which is such a big number that the answer you end up getting is a super small amount of steam. So you end up getting something like 3.36 times 10 to the negative 3, I think, or something like that. Kilograms. This would be about 3.36 grams of water vapor or steam, which leaves us with the mass of the water that's left over being equal to 0.1 kg minus that. So you end up getting about 997 or something. What did you get? Yeah, 0.097. Which would be about 9.7 grams. Nope, 97 grams. Right? Yeah, 97 grams. Liquid water. So that's your final state. 97 grams of liquid water, 3.36 grams of water vapor, and a final temperature of 100 degrees Celsius. T final was 100. Okay, so that's kind of like the next level of difficulty, I guess, for these problems where you have a few unknowns and you kind of just got to think about how much energy you have available and where it's going to go. Anyone have any questions? Well, you proved it for us because you did this calculation, right? And your answer was 106. So that means that it must be... Now there's only... Okay, you ruled out one of the possibilities. One of the possibilities was that there's no phase change. You ruled it out because you got a final temperature of 106. So the next possibility to check is, let's assume that it's a mixture. If we make the assumption that it's a mixture, then we figure out how much water vapor we have. Now, here's the next step. If we had been wrong about it being a mixture, if that assumption was wrong, what would have happened to this mass right here, do you think? Any guesses? Would it be negative mass? Or would it just be I think the mass would just be bigger than this. I think that's what would happen. I think the mass would just end up being bigger than this. So we could figure this out probably pretty quickly by doing some silly things. We could change the initial temperature of the copper. Here, let's just do this real quick. Let's take these two equations and let's see if if I can prove to you guys what's going to happen if our assumption was wrong. You're going to get something silly. You're going to get something. It may be negative mass. You may be right, Tyler. Let's check. So how can we change this in such a way? Looks like I lost the parentheses. There's parentheses on this guy right here. How can we change this in such a way that we actually get all steam? Okay. What would this look like if we get all steam? So we'll change a couple things here. Let's change the initial temperature of this. Let's give it a way hotter temperature. Like, let's make it stupidly hot. Let's say it's 15,000 degrees Celsius. So that this now becomes, instead of negative 50, it's going to be like 15,000 minus 100, 14,000, right? No, 14,900, negative 14,900. I don't even know if that's enough. We may actually have to increase this to 20 kilograms too, just for good measure. Let's assume we have 20 kilograms. This is stupid already because this is higher than the melting point of copper. So this is purely a just see what happens. I'm pretty sure we're going to get an answer here that's bigger than the mass of water we started with, but I could be wrong. I might not have chosen big enough numbers. Yeah, this should work. Yeah, this is a totally ridiculous result. The answer I would get would be that this would be the mass of steam, right? We made the assumption that it's all steam. This would be mass of steam. And the answer I got would be, did I actually divide by negative? No, I didn't. Okay, so it's going to be 51.5 kilograms. So it's not so much we get negative mass, it's just that this is greater than the mass of the water, which was 0.1 kilograms, right? So this equation would be like, oh, you've created some steam out of nowhere, right? So then you would say, oh, this is ridiculous. This is ridiculous. It must be the case that it all turns into steam, all of it, and now we're no longer searching for the mass. What would be the unknown then? This would mean all goes to steam. Goes, probably the wrong word. All transforms into steam. Yeah, exactly. Tyler, you're right. You'd want to find the final temperature now. So let's go back to the original problem and see how these things manifest themselves. So what was our original goal here? Our goal was to find the final temperature and its contents and determine the phase of the water, right? So there's really two unknowns here. The unknowns are our final temperature and the mass of the steam that we have in the system. So you basically work your way through your assumptions. Assumption one is, let's just figure out what temperature the contents would be at if I assume no phase change. That'd be the simplest way to do the problem. That's like the very first problem we did, right? Where you just have two substances and a phase change. So you check, you get the answer. That's wrong. Okay, initial assumption was wrong because it led to an absurd conclusion, right? We work our way through our assumptions. Next assumption, let's assume that everything is a mixture, and let's see where that takes us. So we made the assumption that it all goes to 100 degrees, but some of it gets converted into steam. All right. And with that assumption, we got an answer, and that answer was totally reasonable. That is a totally reasonable answer. It is not a contradiction to any of the starting situations. And we look at the mass of the water right here. That works out, right? So, yeah. I guess one thing... Okay, there were a few questions here. I want to make sure I've answered all these. Koa said, first we need to assume there's no water vapor and then find the T to check the assumption. Is that right? Exactly. That's right, Koa. Ruja said, so in a problem where we don't know if something undergoes a phase change, we can just calculate Q for the substances in the system. If the sum of those Qs isn't 0, we divide by that leftover energy by the latent heat to find the phase change. The first half of what you said is true. The second half is not true, Ruja. You can definitely do that. You can calculate the Qs, right? 3145. This was for the water. This was for the copper. You calculate those. And then what you do beyond that, that just tells you that there's more heat left over from the copper compared to the water, so you get some phase change. You can't immediately assume that you're always going to solve it like this, though, is all I'm saying. Because what if there's multiple objects that are phase changing at the same time? Tom Nook says, how do we know that the steam doesn't get harder? Is it because it's like the water plus ice? Yes, Tom, that's right. As long as there is a mixture of water and steam, they stay at a constant temperature. Constant temperature. Mostly because it can't escape the system. It's a closed system now, right? All right, good questions. A little bit tricky problem, but I think once you know how to do this, the process is pretty rigorous, like algorithmic even. Check to see final temperature for the simplest possible situation. Okay, that didn't work. Okay, check for the next simplest possible situation, which is that there's a mixture. And if that doesn't work, then it must be the case that it all got converted to steam. And if it all gets converted to steam, that is a little more complicated as well. Because, so what would happen if it all got converted to steam? That was this possibility right here. What do I need to add into my equation if it all gets converted to steam? What would I need to add? What would change? You guys already said, come on. Come on, OneNote. You can do it. All right, there we go. So if it all gets converted, yeah, you need the Q for the steam. Exactly. What the? No. Why won't it let me just click things? Okay. So if it all got converted to steam, you'd have to change this to just some final temperature T. And then you'd need to add in one more term. So you'd have 25 degrees down to T, 150 degrees to T. Oh, no, that's not right. I made a mistake. This would be, the water can only go up to 100 degrees Celsius, right? So this would be the all steam scenario. The water would have to go to 100 degrees Celsius. The copper would have to go down to whatever the common final temperature is, which is probably going to be above 100. You need to include the latent heat of fusion, and then the final term would be the Q of the steam, as Ruja says. So now you'd also have to have the Q for steam, and the steam would need to go from 100 up to T. That actually would be the harder part. This would be even harder, technically. I mean, from some extent. And then this would be just the mass of the water. So those are basically the three possibilities. Either the simplest possibility is this one, where there's just two terms. The next simplest possibility, there's three terms, and you're solving for mass. The third possibility is when it all gets converted to steam, and then you get a fourth term, because the steam actually has to increase its temperature. Yeah. Maybe we could find a problem like this from the textbook or something, and we can try it out. But that's all the problems from your guys. Those are all the example problems, at least from the text. Okay. You don't have any questions? Would y'all like to just grab a random problem from the textbook that might be a little more challenging and try it out? What do you guys think? Want to try that? Okay. So let's find one. Oops. University physics. Let's find a problem where we get the last level of difficulty. Okay, really? Okay, I have to get the whole thing on the screen and then it'll let me maximize maybe? So, here. Might take a second to find one. Okay, calorimetry and phase changes.
Probably what we'll do is we'll just go to the end of the chapter. That's usually where the difficult ones are. These dots represent difficulty level 2, right? So if we can find one that has 3. No, these are usually pretty easy, so not surprised. Okay, problems. This is going to be a calculus heat base. I don't know. Those. Let's see. What's this one? You cool a 100-gram slug of red hot iron by dropping it into an insulated cup. So the temperature is 745 degrees Celsius. So this actually might work. By dropping it into an insulated cup of negligible mass containing 85 grams of water at 20 degrees Celsius. Assuming no heat exchange with the surroundings, what is the final temperature of the water? What's the final mass of the iron and the remaining water? This feels like it's going to be exactly the same, right? As what we just did. This feels like, you guys agree this is basically the exact same problem? Because it's just like you've got 100 grams of iron at a temperature of 745 degrees Celsius. It's almost certainly going to be a mixture at this point, right? You can almost tell just by looking at it that it's going to be about the same. We would need a lot hotter initial temperature for the iron, or we would need to have like 100 kilograms of iron. Let's see what else we got. Silly. Hot water versus steam heating. In a household, hot water heating, water is delivered to radiators by this. Yeah, this is kind of a silly one too. We may have to go to a different book. No offense to the publishers, I'm just not. Here we go. What's this one? This might be a really good one, actually. Okay, we're either going to do this one, or we're going to do this one. I think we do this one. Yeah, let's try to do number 17.95. Okay, let's read the problem. It's 11:54. Can we do this in like 6 minutes or so? Let's see. Even if we go over, it's fine. We'll just take a kind of a shorter break. Copper calorimetry can with a mass of 0.446 kilograms contains 0.095 kilograms of ice. The system is initially at 0 degrees Celsius. This may have been one of the problems I gave you on your homework, but if 0.035 kilograms of steam at 100 degrees Celsius and 1 atmosphere of pressure is added to the can, what is the final temperature of the calorimeter and its contents? At the final temperature, how many kilograms are there of ice, how many of liquid water, and how many of steam? So we actually, this is only water. Oh, and copper, I guess. So we got 3 things now. Copper, ice, and here, can I change the color of that? So you got copper, ice, and then steam is added. So is it covered? It has to be covered, right? Doesn't really say. Well, we're just going to assume that it's covered and that we've pumped in steam. Okay. So the steam is at 100 degrees Celsius. You're saying it's a can, so it's closed? Yeah, fair enough. It has to be closed, right? That'd be kind of silly. This is 0 degrees Celsius. It has the mass of... So there's copper, there's steam, and there's ice. The copper is 0.446. Look at that. I hate that it does that. Why would it want me... I don't... Yeah. 0.446
4, 6. Looks awful. Ice is 0.095. Call it MI. Steam is 0.035. So temperature of the steam is 100. Obviously, I guess. I don't know if it's obvious. It's the temperature of the steam initially. Temperature of the ice initially is 0 degrees Celsius. And then copper. Okay, copper is 0. So this starts off at 0 as well. Okay. We're not adding very much steam, right? It's not a lot of steam that we're adding. All right. So what do we got here? Is that all the information? So how do we do this one? So we don't know what the final temperature will be.
What's your intuition tell you? Is it all going to be water? Is it all going to be ice? Probably not all ice, right? Like that's unreasonable, right? Is there a possibility that you have ice, liquid water, and steam? That's not possible, right? It's either going to be ice plus water, only water, or water plus steam, right? Those are our 3 possibilities, right? It's either all water, ice plus water, or water plus steam. Now, the nice thing about the last 2 possibilities is in this case, we know the temperature is 0, right? I don't think that's very likely. In this case, we know the temperature is 100 degrees. And in this case, we do not know what the temperature is. But we know it's all water. And that, in its own way, makes it kind of simple, right? So what I would do is we just test each possibility, right? Since this is a 3-dot problem, I think it's unlikely this is the answer, but let's check. I don't know, maybe it is. Let's check to see if all water is the answer. Okay, so we're gonna look at possibility number 1 first, that everything turns into water. If everything turns into water, what's our goal? It's to figure out what the final temperature is, right? I don't even know if this is a good strategy, but I often think this is one of the best ways to kind of show you how to approach problems. Like you got to go down a certain path and see what happens. So this is our goal, figure out the final temperature here. Then we say something like, okay, we're going to have Q for copper to go from 0 up to some temperature. So from 0 up to T. We're going to have the steam has to transform into water. So we'd have the mass of the steam multiplied by the latent heat of vaporization of water. Here's the thing: should this be positive or negative now? Negative, exactly, because it's going to be going kind of down a state from gas to liquid. The ice, on the other hand, will be positive, and that'll be the mass of the ice multiplied by the latent heat of fusion of water. And then finally, we would need whatever mass of steam we have. That steam, okay, it needs to be basically cooled down. See here, I need to use a different symbol. So now we're going to have the Q for what I'm going to call the steam water. I call it steam water because it's the water that used to be steam, right? And this needs to go from 100 degrees Celsius down to our final temperature T. And then the last thing would be the Q for what? What's the last Q that I need on here? Ice water, yep, exactly. So now the ice that melted into water has got to go from 0 up to T. So these two terms will have a T in them. There's 3 terms with a T, and then there's 2 terms that just have some kind of number here, right? Might be a good idea to actually just calculate what these numbers right here are to get an idea of what's going on here, right? So latent heat of, was it vaporization, was about 2.256 times 10 to the 6th joules per kilogram. The latent heat of vaporization, latent heat of fusion for water is 333,000. So let's calculate what those two numbers are as we put in the other pieces, okay? Can you guys calculate this for me? What is MS, mass of steam, times LV going to be? And what is MI, this times this going to be? So type that in the chat if you guys could. Q copper is going to be mass of copper times specific heat of copper times delta T, which will be T minus 0, minus this term. What do you get? And then plus this term. And we're going to run out of room. These problems, there's so many things to write down. For the steam water, we're going to get mass of steam, specific heat of water, and then T minus 100. And then this one, we're going to get mass of ice. Not specific heat of ice, because it's the ice. The ice isn't changing temperature. And then times T minus 0. All of that equals 0. Okay. Did any of you guys get an answer for what are these two numbers going to be? 78960. $31635. Okay. Now you got to look at these two numbers and ask yourself, where is this energy going to come from? What's the answer? So let's good God, the equation's so big. At least we have two terms that go to 0. I think what we're going to get is something like this. So we've got a T. Let's just group together the T's. T times M copper, C copper, plus mass of steam, specific heat of water, plus mass of ice, specific heat of water. This should all be equal to this minus this. What's that equal to? 31635 minus 78960. 47,325, but it's negative over here, so it'll be positive over here. Okay, that's what you get when you do this minus this and then add it. What else? And then I think it's just this term right here. Plus MS, mass of the steam, specific heat of water, times 100. And that should give us the final temperature. In the interest of saving time, I'm just going to plug all the numbers in. Or you guys can do the same. What do you get for the final temperature? This may not even be right, by the way. Just to keep in mind, this is one possible outcome, and it completely might be wrong. Specific, everywhere it says CW is 4190. Specific heat of copper was 390. Can anyone get an answer for this? I got an answer. I just want to make sure it's right. I got 86. Yeah. Okay. Now, I don't know if that's enough to prove it. I almost think you might need to check these other two cases. But this is a pretty reasonable answer, right? We initially thought that this was probably what would happen, right? The idea that it would all still be steam is kind of ridiculous. And the idea that it would all be ice water would be kind of ridiculous too. Now, it'd be a different story if the steam started off at, let's say, 300 degrees Celsius, right? If the steam started off at like 300 degrees Celsius, well then, you know, that might change what the answer is, because then this whole term, right? If it's just a little bit bigger, you could see how your final temperature might actually not be reasonable, right? But it looks like the assumption we made was correct. How do we make that assumption? We just kind of thought about it. You know, we just like, okay, well, there's some steam. There's not a lot of it compared to how much ice there is. And then we've got this guy that also started at 0 that has to heat up. So it kind of seems to make sense. I think that's the right answer. And this is an odd problem, so we can check it if we really want to. Anyone have any questions? What number is that? 17.95. Oh, it's at the top. Yeah, we're off by a little bit, I guess, but... Oh yeah, and then the answer, of course, we didn't answer part B, but we knew the answer would be. It's just the sum of the two, right? 0.13 is going to be the sum of this plus this. That's 0.13 kilograms. That's a pretty good problem. It's not the hardest type of problem, though, because you need to have a problem where, like, there's a phase change plus a temperature change, where where these don't, like, this, if this didn't start off at 100 degrees Celsius, if instead it was like 120, and if the ice was like, let's say negative 40 degrees Celsius, that would be the next level of difficulty. But this is as hard as it gets for this book, I think. Okay, we're gonna have to take a break. We'll probably take a 10-minute break and then come back and talk about conductivity and heat transfer processes, get through as much of that as we can. So we'll start again at 12:19, and I'll stop the recording.